Today we're going to do 3.1, exponential and logistic functions, part 2. So today we're going to focus on logistic functions. So exponential growth is unrestricted. An exponential growth function increases at an ever-increasing rate and is not bounded above. In many growth situations, however, there is a limit to the possible growth. A plant can only grow so tall. The number of goldfish in an aquarium is limited by the size of the aquarium. In such situations, the growth often begins in an exponential manner, but the growth eventually slows and the graph levels out. The associated growth function is bounded below and above by horizontal asymptotes. These functions are called logistic functions. You guys do not have to write all of that down. I just wanted to explain to you where logistic functions came from. The definition of a logistic function: let a, b, c, and k be positive constants with b less than 1. And a logistic growth function is a function that can be written in the form of f of x is equal to c over 1 plus a times b to the x power, or c over 1 plus a times e to the negative k times x power, where our constant c is the limit to growth. If b is greater than 1 or k is less than 0, we have logistic decay functions. And unless otherwise stated, all logistic functions that we talk about will be logistic growth functions. We're going to be working with both. And then by setting a, c, k, and 1, we obtain the logistic function, which is 1 over 1 plus e to the negative x power. And this function is related to the exponential function e to the x and cannot be obtained by any sort of translation reflections. So what do we need to know from this slide? We need to know these. If b is greater than 1, so our base is greater than 1, or if k is less than 0, we talk about decay. So here, if b is less than 1, we grow, and if k is positive, we grow. All logistic growth functions have graphs, much like the basic logistic functions. Sorry about that. Their end behavior is always described by the equations the limit as x approaches negative infinity of f of x is equal to 0. So we have a horizontal asymptote at 0, and we have a horizontal asymptote as x approaches infinity of c. C is our limit to growth. So our horizontal asymptotes occur at y equals 0 and y equals c, and we have a range of 0 to c. The basic logistic function, just to see what it looks like, we have this shape. As we go towards negative infinity, our graph is going towards 0, which is our limit as x approaches negative infinity of f of x is equal to 0. As we go towards positive infinity, we are going towards 1, which is our c value, and our range goes from 0 to 1. We are increasing from left to right. We don't really have to worry about symmetry, and our horizontal asymptotes are at 0 and 1. If we need to find the y-intercept, horizontal asymptotes, range, and limit to growth, we are going to look at our function 8 divided by 1 plus 3 times 0.7 to the x power. The y-intercept, we plug 0 in for x. So we have 8 over 1 plus 3 times this. Anything raised to the 0 power is 1. 1 plus 3 is 4. 8 divided by 4 is 2. Our y-intercept is 0, 2. Oh, I'm sorry. We have a horizontal asymptote at 0, so at y equals 0. Since c, or our limit to growth, is 8, we have another horizontal asymptote at y equals 8. And then our range, since we have a horizontal asymptote at 0 and a horizontal asymptote at 8, our range is from 0 to 8. Notice how I am using parentheses because 0 and 8 are never actually obtained, so they are not included. Find the y-intercept and the horizontal asymptotes, range, and limit to growth. Once again, limit to growth, I apologize, is 20. We have our y-intercept, we plug 0 in. Negative 3 times 0 is 0. E to the 0 is 1. 2 times 1 is 2. 1 plus 2 is 3. 2 divided by 3 is about 6.67, which is our y-intercept. We have horizontal asymptotes at 0 and c, which is 20, and our range would go from 0 to 20. And that's all for now.